Hi everyone, this is DigWise Technology. Welcome to our Tech Mini class, where we explore the fascinating world of semiconductors. In today's AI-driven world, the industry is shifting from focusing solely on yield to driving productivity through innovation. Today, chip design is about more than cost and efficiency, it's about boosting performance, capacity, and competitiveness. AI plays a key role in this transformation. In this episode, we'll show you how AI optimizes every stage of design and manufacturing, from design margining and timing sign-off, to testing strategies, data analytics, process tuning, binning, and even system-level compensation. Let's dive into how AI is reshaping the future of semiconductors. Let's use this U-Net architecture diagram to explain the semiconductor industry process. Starting from the top left corner with chip design, RTL design, this stage is primarily focused on defining the logical functions of the circuit. Next, during the physical design implementation (APR) phase, the RTL logic is translated into a layout that can be physically realized on the chip. The goal here is to ensure that all logic components are efficiently placed on the chip and that the routing between these components is optimized. Then, the design is handed over to the foundry for fabrication. During this manufacturing process, the wafer undergoes multiple photolithography and other processing steps. With each step, new layers of material or circuitry are added, gradually building up the complete design on the wafer. Once finished, the wafer is diced into individual dies, also known as chips. Chips are packaged and tested, then shipped to customers as final products. So, what exactly is DTCO? Design Technology Co-Optimization (DTCO), as the name suggests, is about integrating design and process technologies to improve performance, power efficiency, transistor density, and cost. It refers to the close coordination and optimization between design and manufacturing processes, aiming to achieve better performance, power, and area. Traditionally, design and process were treated as two separate domains. Designers handled circuit logic, while process engineers focused on fabrication. However, as technology evolves, tighter collaboration between the two ensures that designs can accurately follow new process rules and make the most of cutting-edge technology. This synergy allows for better design optimization and flexibility, even under process variation. To achieve ultimate performance, proactive strategies must be employed. This is where DTCO ML and DTCO Gen AI come into play. Returning to our U-Net diagram, we begin with component data, sourced from sensors embedded in the design. After integrating real-world testing data, this information flows through three phases of traditional mass production. With this data, combined with large-scale chip monitoring and machine learning, DTCO ML utilizes cross-dimensional analysis to optimize chip yield and energy efficiency. This enables strategic binning at shipment, grouping chips by performance level for price differentiation, and applying compensation strategies. Ultimately, the goal is not just yield improvement but a comprehensive boost in competitiveness, productivity, and product optimization, echoing the mission of enhancing productivity. Our aim is to provide innovative chip design tools that support the full semiconductor production chain while enhancing design phase efficiency. However, the industry still faces bottlenecks. Monitoring IP and test data are not yet standardized, and data confidentiality issues create a data acquisition barrier that hinders cross-domain data access and interaction. Sparse testing data also leads to bias in traditional modeling, while high-fidelity simulations are time-consuming and difficult to optimize. This is where generative AI enters as a game-changer, offering the ability to generate meaningful data while preserving confidentiality. Thus, DTCO.Gen AI emerges as a promising development direction, aiming to deliver holistic solutions for the semiconductor industry. So how does it work? Let's look at our DTCO platform in more detail. DTCO ML and DTCO Gen AI. We divide the semiconductor workflow into two stages, pre-silicon and post-silicon. In the pre-silicon phase, we tackle tasks like process analysis, SPICE modeling, and feature extraction. We also customize key components, enhance microarchitecture, and embed on-chip sensors for real-time monitoring and defense strategies. During post-silicon analysis, we use machine learning to assess data patterns, monitor chip behavior, automate binning, and feed insights back into the design loop, creating a feedback cycle that can improve performance efficiency by up to 15% per iteration. In other words, both speed and power efficiency improve simultaneously, creating a positive feedback loop. Under this concept, Digwise Technologies' contribution is to break down the DTCO platform into 4 distinct tools. LibMetric analyzes standard cell libraries, evaluating timing, power, and area, to help designers make informed decisions early. GRO Compiler, a user-friendly RO compiler that simplifies configuration and circuit synthesis for delay line creation. Copernic, a performance analysis tool that visualizes multidimensional data and helps optimize process parameters and yield. Binning PG, a machine learning-powered tool for systematic chip binning, grouping similar performance chips to maximize product value and efficiency. Next, the breakthrough of DTCO.Gen AI will accelerate the development of EDA tools, enhance production efficiency, reduce costs, and improve quality. In line with advancements in generative technologies, we currently offer 2 key tools: high-dimensional data modeling with generative adversarial networks, GANs, and diffusion models. These technologies enable virtual chip data to capture microscopic data distributions and covariances across multiple dimensions. At the macroscopic wafer level, they also reveal the potential impact of system-level defects and variations. This allows us to precisely manage design margins and improve chip performance and power efficiency. By leveraging virtual silicon data as a critical assistive tool in DTCO, we aim to bring transformative change to semiconductor design and manufacturing. Finally, thank you for watching. We hope this tech mini-class was insightful. If you have any questions or are interested in our tools, feel free to contact us anytime.